good to know how things are actually used in practice. And he certainly has a lot of experiences in various sorts of optimization in practice. And so he's going to tell us about mixed integer programming and some ideas that are useful and maybe some that aren't and what actually works and so on.
Thank you. So thank you for the invitation to speak. Actually, is the microphone on?
Yes.
Okay. I'm going to give a fairly broad overview of how effectively, take a fairly broad look at the question of how effectively we can use multiple processors in practice for solving LPs and MIPs, linear and mixed integer programming problems. Just to make sure we're all starting on the same page, I'm sure this is familiar to everyone. I'll go quickly through it. An LP is an optimization problem of the form minimize C transpose X subject to AX equals B, X between lower and upper bounds. So linear objective, linear constraints. Mixed integer program, a MIP, is an optimization problem of the same form with the addition of a constraint that some or all of the xj's can be constrained to take integer values. Binary values are most common, but arbitrary integrality restrictions are fine. All right, if you look at LP and MIP in practice, there's really, there's pretty substantial motivation for trying to understand how to do these well, basically how to solve large problems, how to solve them quickly. There are really three important characteristics that these approaches share. They're broadly applicable, computationally demanding, and the solutions have significant financial value, millions of dollars potentially at stake. So I'm going to talk about each of these in turn. So on the topic of applicability, one thing we did was we just took a list of all of our customers for a one-year period and tried to classify them by application area. So this is basically 2012. There are a few that are in bold. Actually, those are maybe a bit harder to see. The bold ones are the ones that are more common. So electrical power, energy, finance, logistics, and workforce scheduling are more common. But as you can see, it's an extremely broad set of applications for the technology. And this is just 1 year worth of applications. As far as the computational demands of LP and MIP, let me talk about each of these in turn. First, I'll talk about LP. To talk about computational demands, it's useful to talk about the actual algorithms that are used. For LP, as you probably know, there are two primary algorithms. There's the simplex method, and there's interior point, or otherwise known as barrier. So here's a trivial example. This is a problem in two variables with three constraints, plus the non-negativity of the two variables. And the blue region is the feasible region for this problem. And the simplex method traverses vertices. So it moves from one vertex of the polytope to another along an edge. In order to improve the objective, eventually it reaches an optimal vertex. Interior point, on the other hand, traverses the interior of the feasible region. It follows something called a central path. So the central path is actually, it's got fairly interesting shape typically. You can't follow it directly, so you do you linearize. You basically use Newton's method. So you compute a step direction, you do a predictor step, you do a corrector step, and you repeat. Oops. And this will, so interior point method will eventually reach a point that is near to the optimal face. It'll actually reach a point that's near to the middle of the optimal face of the polytope, of the LP. So in terms of computational demands, LP is actually mostly a solved problem. So if your goal is just to solve a single LP problem, it's extremely rare that that presents a major challenge. There are a few LP models that we've gotten from customers that we just can't solve, but I can count them on probably one hand. However, that doesn't mean that LP itself is not a computational bottleneck. In particular, LP is often used as a subroutine, and oftentimes the results of one LP solve are used as the input to the next LP solve. So let me give a concrete example. This is a model called SGM. It's a scheduled generation model for an airline. Modest size, about 150,000 rows, 180,000 columns. It's actually a MIP model. So if you look at the LP relaxation of the MIP model, the root node of the MIP, took about 18 hours to solve. This is actually a couple of years ago, probably now it'd be quite a bit less. But. And then that solution, of course, was a continuous solution, didn't obey the integrality restrictions. But a bit of branch and bound was enough to guide the solution towards feasibility. After 1,700 nodes of branch and bound, the first feasible solution to the problem was found with a 3.7% optimality gap. So the maximum improvement that would be possible from this solution was bounded at 3.7%, which from the customer's point of view was an acceptable gap. So this was an acceptable solution to their problem. What wasn't acceptable was the 92 days of runtime that was required to reach this. And so this is an example where basically it is a MIP, but the bottleneck is just solving a sequence of LPs. So thus, LP is mostly a solved problem from a computational point of view. When it comes to mixed integer programming, actually this is partially a repeat of what Cindy did yesterday, but
Question?
yes.
So the few examples where you couldn't even solve the LP, can you say more? Were they just too big?
Actually, typically it's numerical issues. Just the lack of, basically the inability to make consistent forward progress.
So precision issues?
Yes, yeah. So when it comes to MIP, the standard solution approach is a branch and bound. So you start off by relaxing the integrality constraints, giving you a root relaxation. You solve that as an LP. And the objective function for that LP, we're assuming minimization, so the objective function for that LP is going to be lower than the objective for the optimal integer solution. Clearly, the relaxation has fewer constraints, so if we add the integrality constraints back in, it's going to make the objective worse. So the LP relaxation is presumably going to have variables that are required to take integer values so it's the model is going to have integer variables that do not take integer values in the LP relaxation. So in this example, we have a variable v, which is constrained to take an integer value. In the relaxation, it takes a value of 3.5. So you branch. You branch up, you branch down, you add additional bounds. In the left branch, v less than or equals 3. In the right branch, v greater than or equal 4. And you continue this branch and bound process. So each of these subproblems here is a MIP itself. It's the same as the original MIP, but it has one additional bound. And so we just recurse. So we take this problem, solve the relaxation, choose an integer variable that doesn't take an integer value branch. Eventually, one of three things is going to happen as you continue this process. One possibility is you may discover that the relaxation at a particular node in this branch and bound is integer feasible. All the integer variables take integer values. That becomes your incumbent. It becomes an upper bound on the solution for the MIP. As you continue, you explore more nodes. Maybe you find another node that has an integer relaxation, and that node has a better objective value than your previous integer solution, so that becomes your new incumbent. You get a new upper bound. You may discover in a branch that the relaxation for a particular node, the objective value is worse than the objective for the best integer solution you found, in which case you can fathom that node. You can ignore that subtree. You may discover that a subtree is infeasible, in which case, of course, you can ignore that subtree as well. At any point in the branch and bound process, you'll have a lower bound, which is going to be the objective bound for the worst sorry, it's going to be the worst relaxation value for any unexplored node in your tree. So basically each, at any point you have what's called a frontier, a set of unexplored nodes. And the node among those that has the worst bound is basically going to constrain your, overall bound. So as the branching bound progresses, you have an upper bound, you have a lower bound, you have an optimality gap. And as the exploration continues, the gap shrinks. Eventually, the gap reaches 0. That's a proof of optimality. Typically, people stop well before that. So typically, they're content with a non-zero optimality gap. So MIP, I probably don't have to say this, but MIP is definitely not a solved problem. So here's one extreme example. Here's a customer model with 44 constraints and 51 variables. The variables are all general integers. Modest size problem. If you solve the root node, it's fairly easy to find a integer feasible solution with objective 2186. This is found with a heuristic approach. The initial upper bound is negative 1379.4. You let this problem run for a day and a half, several million nodes, several gigabytes worth of tree data, and the integer solution and the lower bound do not change in that time. So that's an extreme case. So I should say that this is unusual. A problem of this size is typically quite easy, but I mean, MIP is NP hard, so there are going to be cases that are just extremely difficult. So I talked about generality. I talked about computational cost. Let me talk a bit about financial impact. There are lots and lots of examples I could give. I'll just give one here. So the NFL, National Football League, is a $9 billion a year business. And the profitability of their $9 billion a year business is heavily dependent on the solution to a single mixed integer programming problem. And when I say a single problem, I'm not talking about solving a family of models. I'm not talking about solving a sequence of models. I'm talking about a single instance, one MIP model. So what does this MIP model do? This MIP model determines the schedule, which teams play on which days, which ones play Monday Night Football, which ones play these time slots, those time slots. So the schedule determines basically how many people are going to watch the games, which determine how much they can charge for advertising for the games, which determines how much the TV networks will pay the NFL for the rights to carry the games, which has a tremendous impact on their bottom line. So this is one example. There are many other examples. Basically, LP and MIP have tremendous financial impact. So if you look at the landscape, so we've got a technology that's broadly applicable, computationally demanding, and the solutions have significant financial value. In addition, if you look at the algorithms, on the surface, there are actually some obvious sources of parallelism. So this seems like a recipe for large-scale computing. Basically, throw lots of hardware at the problem. And as I'll discuss, the reality is that parallel computing has actually had a pretty limited impact on the practice of optimization. So I'll talk about parallelism in linear programming first, and then I will talk about parallelism in mixed integer programming. So as I mentioned, in linear programming, there are two different algorithms typically used, simplex and barrier. Let me talk about the steps associated with each of these algorithms. So in simplex, the basic algorithm maintains a basis, which is a square submatrix B of the constraint matrix A. So at any point, the algorithm has a basis, and it has an LU factorization of this basis. In each iteration of the simplex method, you choose an entering variable. So you choose a variable that's not currently in the basis, where bringing that variable into the basis would improve the objective function. You compute a direction vector, which is basically the change in your current X solution for each unit change in the entering variable. You compute a step length. It's called a ratio test. Basically, you determine how far you can move in that direction before one of the other variables hits, one of the affected variables hits one of its bounds. And then you bring the entering variable in, you take the variable that hits its bound, you bring it out. You push it out. And so when you do this, you get a new basis, so you update your basis factor. Basically, you perform a bunch of updates to account for the fact that you've changed your basis. And then these updates accumulate. Periodically, it makes sense to just throw out the updates and just refactor. So you just do a new LU factorization of your basis B. So simplex in one slide. The barrier algorithm, it's quite different. It actually solves a series of weighted normal equations. So in each iteration, you solve a linear system involving the matrix A theta inverse A transpose, where A is your constraint matrix, theta is a diagonal matrix, and so the resulting matrix is a positive definite, symmetric positive definite. So this is these systems are solved using Cholesky factorization. Yes, Jim?
So we should think of these as sparse problems in general?
Yes. Oh, yeah. Always. Yes. So these are solved using the linear systems are solved using a Cholesky factorization and a forward and backward solve. So the first step in barrier is to compute a field-reducing ordering. So the matrix that's factored in each iteration has the same structure each time. And so you can pre-compute this ordering once. This is to reduce the cost of the factorization, reduce the amount of fill that results in the factorization. And then once you've computed this in each iteration, you form this A theta inverse A transpose matrix. You factor it. You perform one or, well, typically several solves involving the factor matrices. Do a few AX and A transpose X computations, a few vector operations. And then there's a final step here, which is called a crossover step. So the interior point method remains in the interior for the entirety of its execution. And so you never actually reach the optimal phase. So what the crossover step does is it takes the final iterate, which is presumably quite near to your optimal phase, and it moves to a vertex of the optimal phase. And so when you're all done with barrier, you have a basic solution. It's really impossible to tell if you're given that solution whether it was computed by barrier or simplex. So for any LP and MIP model, there's actually a first step, which I haven't mentioned so far, which is a pre-solve step. Basic notion here is that optimization models, LP and MIP models, are built by people or programs or what have you. They typically have some simple reductions that can be performed on them. Things like variables that are fixed. So, if a variable is fixed to a particular value, you don't want it sitting in your constraint matrix. You just want to pull it out once at the beginning and not have to deal with it again. Constraints that are trivially satisfied, those can be removed. Equalities. So if you have x equals y plus z, you may want to remove the variable x and just replace it with y plus z wherever it appears. So there's a list of pre-solved reductions. These are basically just logical reductions. You do the problem to simplify it, to make it smaller, so that the simplex or barrier algorithm have a smaller problem to work with. And then once simplex or barrier computes a solution, there's an unpre-solved step where you take the solution to the pre-solved model, you transform it to a solution for the original. So if you look at the steps associated with simplex and barrier, in terms of iterations, simplex, the iterations are incredibly cheap. The basis matrices that are factored in simplex, in most cases, they're mostly triangular. And so the LU factorization of a nearly triangular matrix is quite cheap. Triangular solves involving these matrices, these are the vectors that are being solved against are sparse. The matrices are extremely sparse, so these triangular solves are very cheap. The number of iterations you do in simplex is order thousands, order millions, depends on the problem, but lots and lots of cheap iterations. That's the key point. When it comes to barrier, the iterations are much more expensive. This is a set of weighted normal equations on the full A matrix, not just on a basis matrix. However, there are not nearly as many iterations required. So barrier, the typical iteration count is dozens. 50, maybe 100. In terms of the sparse linear algebra, in Simplex, as I mentioned, the triangular solves are on very sparse matrices, and the matrices are constantly changing. So we're constantly pivoting entries into the basis, pivoting entries out. In contrast, for barrier, you're doing a Cholesky factorization on a matrix with static structure. So Cholesky factorization can exploit dense kernels, level 3 kernels. So this is it's a much more amenable to sort of high performance kernels, things like BLAS3, that sort of thing. Jim?
So in Simplex, then, from one step to the next, it's a low rank update, and you want to update the LU factors cheaply.
Correct. So when it comes to parallelism, for Simplex, there's really no general purpose parallel algorithm that's been proposed. There have been a few special purpose Simplex codes for matrices with special structure. Even these haven't been that successful. But in general, when it comes to just an arbitrary matrix, there's really nothing that's been proposed for Simplex. When it comes to barrier, if you look at the computational bottlenecks, you got Cholesky factorization. It's well known how to do parallel Cholesky factorization. Triangular solves, even that you can parallelize. Matrix vector multiplies, even the ordering. There's parallelism in the ordering. So lots of opportunities for parallel computing. So let's compare the performance of these two approaches on a set of models. So this is on a set of 1,242 test models. Basically, we receive models from customers, we collect them, we have our own internal test set. So some of these are public benchmarks, some of these are models that people have sent us. And just to create a reasonable test set, basically we threw out the models that were too easy or too hard. What does this mean? What does too easy and too hard mean? We just arbitrarily said that any model where both barrier and Simplex can solve it in less than 0.01 seconds, it's not even worth trying to measure. And just to keep the test tractable, any model where neither of the two algorithms can solve it in 2 hours, we just exclude it. Leaves about 810 models. And then what we do is we run Simplex on the model, we run barrier in the model, we take the runtime ratio and then take the geometric mean across that full set of models. And given what I've said so far, you might expect barrier to win by a large margin, given the fact that this test is run on a 4-core machine. It's just a modern, it's basically a PC, the latest version of Gurobi running on a quad-core i7 3770K. Barrier uses 4 cores. We include the time for the crossover. Simplex uses 1. We use dual Simplex here. There's actually a primal Simplex and a dual Simplex. Basically, primal Simplex uses the Simplex algorithm on the original problem, as stated. Essentially, dual Simplex dualizes the problem and applies Simplex for that dual model, but the dualization is implicit. So dual Simplex, for various reasons, is much faster than primal Simplex. So dual Simplex is the default Simplex choice. And we just arbitrarily set the dual Simplex as the baseline, so the geometric mean of Simplex versus itself is 1.0. And what you see is barrier is about 5% faster on average on this set. However, dual wins more often than barrier does. So a bit of this is actually a function of the notion of what is a model that's too easy. So barrier, there's a fair amount of startup cost associated with barrier. You basically do, pre-ordering. Basically, you are paying a startup cost in barrier, which is not so big in Simplex. So as the problems get more difficult, so as we vary the notion of what makes a problem too easy from 0.01 seconds to 0.1 second or 1 second, barrier actually starts to pull ahead. So you can see so the first line here was the number from the previous slide. And then as we get down to 1 second, barrier here is winning nearly twice as often as dual Simplex, but not always. And on average, it's about a factor of 2 faster than Simplex. And so based on what I've said so far, you may conclude that this is a result of the fact that barrier can exploit parallelism. that it can make use of multiple cores. And that's actually not really the main part of the explanation. So the explanation is more related to this chart right here. So what this shows is peak double precision gigaflops for several generations of processors. These are just, cheap desktop processors, latest generations. So going back to 2001, Pentium 4, 2008, 2011, 2013. What you see is a pretty impressive improvement in the peak double precision floating point for these chips. And the computational kernel in Barrier is basically a BLAS3, is a matrix-matrix multiply. So it gets a substantial fraction of the peak performance. And so even in the last 5 years, the performance here, and this is a 4-core chip. This is a latest, Haswell 4-core chip. The performance has increased by a factor 10. Whereas if you look at simplex performance, generally simplex performance scales with the clock speed, roughly. And so in this 5-year period from 2008 to 2013, the clock speed has gone from 2.4 to 3.5 gigahertz. So we're talking about a factor 10 improvement in the capability of these chips for the computational kernel of Barrier, and less than a factor 2 for simplex in the same period.
Isn't the reason that they're much faster now because they have much more internal parallelism in the vector units?
Sure.
Okay.
Sure. Actually, so going back to the question of thread-level parallelism, basically core-level parallelism, how much parallel speed are we getting in the Barrier solver? What you see is maybe a bit surprising. So for 2 cores, on average, we're getting about 1.29x. 4 cores, 1.51x, and 12 cores, only 1.7x. So what's going on here? So one way to look at this is to look at a breakdown of where runtime is spent. So these are fractions of total runtime. So for example, pre-solve, when run on 4 cores, over this set of models that take more than 1 second, pre-solve on average takes about 12% of total runtime. And these are the top 5 consumers of runtime in the Barrier solver. And what you see is that indeed on 4 cores, factorization is the number 1 item, the number 1 consumer runtime, but crossover is just behind it. And then on 12 cores, factorization has actually fallen off quite a bit, and crossover has increased quite a bit. So I haven't said to this point what crossover is, what the algorithm is. And, well, the algorithm is basically simplex. It's a special case of simplex. There are a few steps in simplex that can be skipped. But basically, you have a current basis. You're pivoting variables in. You're pivoting variables out. You're maintaining LU factorizations, doing basis updates. It's simple. From a computational point of view, it looks just like simplex. And so
factorization is what would be in the dense case n cubed, and solve would be n squared. In the sparse case, they're almost the same. Is that the correct interpretation?
Oh, yeah, you're talking about these two?
Yes, comparing those two. So the solve is just one right-hand side or lots of right-hand side?
Yeah, it's actually you stated it in a sort of asymptotic way. It's more a constant factor thing. I mean, the factorizations are running at 150 gigaflops, whereas the solves are running at 1/20th, 1/50th of that.
Because they're BLAS 2-ish as opposed to 3.
Yeah, right, exactly. And so there are some constant factors, and actually that comes in the next slide. So let me show the next slide. So again, all the results here are relative to our notion of what constitutes a model that's too easy to consider as part of the benchmark. So what I've done here is varied the notion of what's too easy instead of, so we started at 0.01 second, 0.01 seconds, we moved up to 1 second, now we're going all the way up to 100 seconds. And as you might expect, the bottlenecks are going to shift as you move to more difficult models. And indeed, the cost of the factorization relative, in particular, to the solves has increased. However, the biggest shift is happening in the crossover. So basically, what's happening is this sequential thing, this simplex thing, is coming to dominate. And so when we talk about barrier versus simplex, it's not really a direct comparison. It's simplex versus barrier with some simplex. So simplex is really the computational bottlenecks in both cases. And you could reasonably ask, well, do I absolutely need to do crossover? Why can't I just take the interior solution? And you could. Empirically, what we find is that basically the interior solutions are just not actionable. You just can't put them into practice. Simple explanation is a basic solution, most of the variables sit at bounds. So in particular, if your bounds are just lower bounds on the variables, most of your variables are going to be sitting at 0. So if you're coming up with a plan for a factory or an allocation of resources, whatever, this is going to give you a compact set of actions. Whereas an interior point solution, none of the variables are sitting at a bound. The solution is in the interior of the polytope. And so these are just, there are many reasons why people just can't act on these solutions and need a basic solution. Yes?
So when you do the crossover, it's conceivable that many of the constraints and variables might have become irrelevant because you're at an interior point that's somehow near a corner, say.
Sure.
Does that happen, or do you generally find that you don't really save anything? You can't throw away variables, you can't throw away constraints.
So the algorithm, the sparse linear algebra in the algorithm exploits that. So a constraint that is not active corresponds to a slack variable being the basis. And a slack variable in the basis, basically, that just takes a portion of the basis and makes it the identity matrix. Which, from a linear algebra point of view, doing factorizations and solves and such on an identity matrix is awfully quick.
So you don't get any sort of essentially dimension reduction, like you might imagine starting with.
Well, you do, but the dimension reduction just comes from the fact that there's a large portion of the matrix that's an identity matrix. And so effectively, it's not complicating. It's not participating in any of the expensive sparse linear algebra stuff.
I also had one question from a slide before. You said that when simplex is iterating, it maintains sparsity. And is that an artifact of the problem structure, or can you generally guarantee that? It seems like with networking-related problems, you might maintain sparsity in a natural way, but generally, as simplex continues, you would expect the matrix to kind of fill out.
Yeah, I mean, it is an empirical. You can construct matrices that behave badly, absolutely. So it is an empirical statement, but it's nearly universal. Okay, so when it comes to parallelism in LP, so the benefits for barrier tail off pretty quickly, actually. But there is another way to exploit parallelism. It's fairly simple. It's concurrent optimization. When you've got multiple algorithms to solve the same problem, just start a horse race. Start all the algorithms. The first one that finishes wins. If you look at computational results, again, this is on a 4-core system. In this case, we're going to use 3 cores for barrier and 1 core for dual simplex. And the geometric mean here comes down from 0.49 for barrier alone to 0.38. So a pretty substantial improvement here. Of course, this is not a recipe for massive parallelism. We've only got 3 different algorithms for solving these LPs: primal simplex, dual simplex, and barrier. And primal is actually sufficiently worse than dual that adding it to the mix doesn't really buy you anything. So this is a way to get 2-way parallelism. All right, so I'm going to talk about mixed integer programming now. So on the surface, when it comes to mixed integer programming, it's embarrassingly parallel. You got a search tree, you got a bunch of nodes on the frontier. These nodes are independent. You can form them off to multiple processors. What's the problem? If you look at the reality, so here are results from a industry standard test set, MIP 2010. Set of models that were collected to try to be representative of the models that people are actually solving. What you see is on 4 cores, average improvement is 2.2x. 12 cores, 3.3x. So some speed up from parallel, but nothing like what you'd expect given the embarrassing parallel picture I showed on the previous slide. So here's another way of looking at the speed up results. I'm sorry, I should say that there are actually several factors that come into play that limit the parallelism for MIP. I'm actually going to talk about just one. This one's the easiest to understand. It's probably the most intuitive, and it is probably the most severe as well. So if you look at parallel speedups across the model, so these are number of nodes explored on the x-axis, parallel speedup on the y-axis. Each point represents a single model in that set of 87. And what you see is for models that explore fewer than 1,000 nodes, the parallel speedup is non-existent. And this set here represents about 1/3 of the models in the set. And intuitively this makes sense. Basically, the parallelism, the source of the parallelism is the nodes of the tree. If there aren't that many nodes, there's not that much parallelism. As you increase the number of nodes, the parallelism increases. You notice that there's actually a fair amount of noise in these results here. So for any one node count, you may see a pretty broad spectrum of results. Let me just comment on that briefly. So one thing that's inherent in solving mixed integer programming problems, no matter how you look at them, no matter what you do, is noise, random noise. Let me show you one result here. So there's a model 60WA01, where if you solve it using default settings, the runtime is 509 seconds. If you change a parameter, you set the seed parameter to 2, runtime is 23 seconds. So 22-fold speed up. What is this parameter doing? It's just changing the random number seed. So the nature of mixed integer programming, there are a variety of decisions that have to be made in order to solve a mixed integer programming problem. You have to decide which variable to branch on, which cuts to generate, which heuristics to apply. There are a variety of decisions that must be made. And oftentimes the criteria that are used to make these decisions, basically if you're considering multiple candidates, it's a tie. So you basically break these ties arbitrarily. A different random number seed gives you different tie breaking, which sends you down a completely different path. And sometimes the one path is radically better or radically worse than another. And so in this particular case, I didn't change anything other than the random number seed. So same model, same processor count, same algorithm, same everything, just the random number seed. So you can imagine if you change anything at all, it introduces a substantial noise component. So let me go back to the previous set of numbers. Let me present them in a different way. So again, 1 point per model in the data set. In this case, the x-axis shows the fraction of the runtime that's spent at the root node when run on one processor. So 1.0 means all of the time was spent at the root node. Down here means a small fraction. Again, what you see, of course, is that if you spend a large fraction of your runtime at the root node, there's not going to be a lot of opportunities for parallel. Assuming that you can't parallelize the root effectively. I'll get back to that. What's perhaps more interesting is if you look at the full set of models, for the majority of models, they're spending a significant fraction of total time at the root node. So, if you just a simple Amdahl's law computation says that if you're spending 20% of your total runtime at the root node, then your maximum speed up is going to be a factor of 5.
Question.
Sure.
So the title says p equals 12 and the caption says p equals 1.
So yeah, the fraction of runtime was measured on p equals 1, but the speedups here were measured for p equals 12.
What's speedups percentage?
They're ratios, so 10x, 8x.
So with 12 processors, you're getting a 14-way speedup.
In some cases, yeah. I mean, that's that noise component coming into play, right? And so, clearly not all nodes are created equal. If all the nodes had the same cost, then all you'd need is 100 nodes to get a 1%, to have 1% of your time spent at the root. So clearly there's some pretty expensive things happening at the root node. So search tree looks more like this. So what's happening at the root node? So a lot of things. Pre-solve, as I mentioned. Root relaxation solution, so you have to solve the root relaxation as an LP. The solution at the root is much more expensive than the solution at the nodes, because at the root you have to start the solution from scratch. Whereas at the nodes, all you've done from a node to its child is change one bound, and Simplex can re-optimize quite quickly. So that's a lot faster than solving from scratch. At the root node, you're generating cutting planes, you're applying heuristics to try and find feasible solutions that satisfy the integrality constraints. Symmetry detection, branch variable selection, there's a long list of things that are done at the root node, and the list keeps getting longer as the technology improves. And the basic motivation for doing all these things at the root node is if there's something that's true about the problem, you're better off discovering it once at the root node than rediscovering it at every node in a branch and bound tree. So let me give you an example. This is an example of a cutting plane. It's actually, it fits the theme of one of the minor themes of the conference. It's triangle detection. So imagine you have a set of binary variables x, y, and z. You have a set of constraints x plus y less than or equal 1, y plus z less than or equal 1, and x plus z less than or equal 1. So these are pairwise incompatibility constraints. One of these two variables has to be 0. Okay? If you look at the relaxation solution, a solution where all your variables take a value of 0.5 is feasible. However, if you have a set of variables that are pairwise incompatible, then clearly only one among that whole set can be chosen. And so this constraint is actually valid. X plus y plus z less than or equal 1 is valid for this problem. And this constraint here cuts off this solution. X equals y equals 0 equals 0.5. And so in general, what cutting planes do is that they add redundant constraints to the problem. The constraints that don't change the set of feasible integer solutions, but change the set of feasible continuous solutions to get a tighter relaxation, a relaxation that more closely matches the set of integer feasible solutions. And the process of adding cutting planes, you solve the root relaxation. You add a set of cutting planes to cut off that root solution value. You resolve, respecting those cutting planes. You cut that solution off. You repeat this process. There are 13 different cutting plane routines in Gurobi. And so this process is basically, and it turns out that finding these violated cutting planes is actually cheap. The expensive part is re-optimizing, and that's Simplex. Another thing we do at the root node is symmetry detection. So it turns out it's quite common in mixed integer programming problems to have automorphisms, to have permutations that basically map the model back to itself. So given a model C transpose X, AX less than or equal B, an automorphism is a row permutation and column permutation that maps the constraint matrix, the objective vector, and the right-hand side back to itself. So what can you do with with this information? Well, you can do a lot of things. Sort of probably the simplest thing to imagine is, let's say you're in the middle of a branch and bound search. You visit a node, and you discover that the node you're visiting is isomorphic to a node that you've already visited. So that means that every solution that is derived from that node, that you find in the subtree rooted at that node, is going to be isomorphic to a solution that would be found by exploring the other node. And so there's actually no reason to explore both of these subtrees. You can just explore one of the subtrees, and you can find all the solutions in the other subtree just by applying permutations to the solutions you found in the original subtree. And of course, in order to exploit this, you need to identify these automorphisms. So there's there are algorithms for doing for finding graph isomorphism. They're not cheap. And if you're going to exploit this information, you're going to have to find these automorphisms at the root node. So an obvious question at this point is, if you're working in parallel, there are all these things that are happening at the root node. Are they really essential? Is it reasonable to consider just skipping these steps and just assuming that using multiple processors will make up for any potential loss? And in fact, I'm going to argue that the trend is actually moving in the opposite direction. So even in the presence of parallelism, the amount of work associated with solving mixed-integer programming problems is moving. The work associated is moving to the root and away from the nodes. So let me talk a bit more about this. So I'll just, how am I doing on time? I'll just go through this quickly. So these are MIP speedup numbers going from 2009 to the present. This is for a set of MIP models that take more than 100 seconds. What we're doing is we're computing version-to-version improvements for various versions of our product. And just to say, none of these versions of the product were behind the state of the art. So this is not us catching up. This is really the progress of the state of the art. And so if you look at the cumulative improvement over models that take more than 100 seconds for this 5-year period, it's basically a factor 21 average improvement in our ability to solve models that take more than 100 seconds. Okay, so the technology keeps improving. There are a variety of factors that come into play when it comes to the improvements in the product. One factor that does not come into play is we haven't figured out how to solve nodes faster. So, simple process of deduction. If we are not solving nodes any faster and we're solving problems much faster, that means we're solving fewer nodes. So basically, the amount of work that's being done in the nodes is shrinking. So as the technology improves, the opportunities for parallelism by exploiting the nodes, the size of the tree are decreasing. So where are there increasing opportunities for parallelism in MIP? Well, one opportunity is concurrent MIP. This is basically it's a similar idea to concurrent LP. So in the case of LP, we had multiple different algorithms. We set up a horse race. Whichever one finished first won. In the case of MIP, we don't really have different algorithms, but we have different strategies within the algorithm. So you can certainly imagine on one core exploiting a strategy that is more aggressive on cutting planes, another core less aggressive, more heuristics, less heuristics, different branch variable selection. There's a long list of strategies that are employed.
Different random number generators.
You're reading ahead. Yes. So it turns out that the most effective strategy we've found so far is, in fact, just to set up different random number seeds. So just fire off multiple machines, same exact strategies, same exact model, same exact everything. The only difference being different random number seed for each machine. As you might imagine, this approach does have its limits. So you're not going to get, this is not going to be an effective way to use 1,000 cores. But on 5 cores across this MIP-lib set for models that take more than 100 seconds, get a 1.72x average improvement in performance. Starts to tail off, so if you use 25 machines, the improvement is only 1.89x. So when it comes to, so far I've really only talked about, I've looked at averages across sets of models. And the picture is not so encouraging when you look across these sets, but there are definitely models where large search trees are explored. And in order to solve the best known approaches to solving these problems require you to just plow through hundreds of thousands or millions of nodes. And so I just wanted to say that this simple distributed scheme, this embarrassingly parallel aspect of MIP, sometimes works. And so here are results for a distributed memory version. This is just a bunch of machines sitting on an Ethernet. Nothing. This is not a supercomputer or anything like that. So on 4 machines for this set of 3 models that require, these models require order 1 to 10 million nodes to solve. So on 4 machines and 8 machines, we get nearly linear speedup. Things start to trail off at about 16 machines. There are no doubt, problems that require hundreds of millions or billions of nodes that would be able to exploit more machines. But again, this is not, this is going to get us to order dozens of machines. It's not going to get us to thousands of machines. So actually, to conclude, we have customers who are literally begging us to give them a solution for huge models that they'd like to solve, and they're willing to buy whatever hardware it takes. The data's there. I mean, they're generating huge models. The money's there, so the financial value of solutions to these models is substantial, is enough that they're willing to buy whatever hardware it takes to solve these problems. But despite what on the surface seem like pretty obvious sources of parallelism, if you dig a bit deeper, you discover that they're not so obviously general purpose. And in fact, despite these sources of parallelism, really parallel computing has played a fairly modest role. We're talking speedups in the 2 to 5x, certainly not the tens or thousands that ideally you would hope for with parallel computing. So that's it. Thank you.
All right, so lots of questions, but are there any other questions?
Yeah, I'm curious about 2 things about sort of the asymptotic performance. One was, in your talk, you labeled the instances as sort of hard and easy on a long spectrum. Does that correlate for the first part of your talk when you're not doing integer programming? Does that correlate with problem size, the non-zeros, or is that just simply running time of your algorithm?
I mean, it depends. So it depends on the algorithm. So for barrier, generally, it's going to for the barrier iterations, it's going to really depend on essentially the density of the factor matrix. The number of iterations in barrier is nearly constant. And so, yeah, the runtime is going to be determined by the cost of solving the system.
Filter, like at least 0.1 seconds, at least 1 second. You're using what reference frame as is it
Just a particular machine.
any particular algorithm or?
Well,
You
so
would set it by problem size. You wouldn't say I'm just going to take all the large problems. You
Right.
would say,
right, and it was just so the set was chosen in a way we tried to be careful not to bias it towards one or the other, but yeah, the sets were basically chosen by runtime on a particular machine, excluding models where either algorithm took more than a certain time. It's just
My second question
it's
is, I'm really interested in the large instances, like the ones in the first part of your talk said were really hard, they're going to take like 2 hours. And I'm curious about how you, in practice, you see the asymptotic running time growing. So for example, in Simplex, in my experiments, at first I thought it was growing like, if you had an n by n matrix and it's reasonably dense, I thought it was growing maybe like into the 4th. But then as n gets larger, it seems to change. And with barrier, I don't really have an idea either. In all cases, it seems to be super linear in the number of non-zeros. But
Sure.
I'm wondering what your experience is.
It's unfortunately it's so problem dependent. There are classes of problems where in barrier you can characterize the growth rate, and it's absolutely super linear. But when it comes to simplex, there's very little theory about iteration counts.
Yeah, the theory is way off compared to the practice.
Right,
So
right.
wondering about practically.
It's so problem dependent.
My reasoning on this was that both simplex and the interior point methods essentially at least need to solve system of equations.
Right.
And that's not something we know how to do in linear time, say the number of non-zeros. So,
Well, I mean, for a lot of these problems, they have substantial network structure. And so, you know, the LU factor of a network problem is, you know, it's triangular
so once you do that.
for the basis of a network problem.
And how long does that step take? Is that,
So the factorization is going to be it's going to be linear in the number of edges, right?
okay, so if it has a nice structure, then maybe you can get linear.
Sure,
Yeah.
sure. But you know, there are very few pure network problems. There's always some sort of side constraint, and there hasn't been that much work in trying to characterize, you know, exactly what are interesting classes of side constraints, that sort of thing.
I want to get back to something that Jim asked about what makes difficult problems difficult, especially the crossover. Because presumably you cross over once you're, you know, the gap is small and you're close to the optimal solution. So is this because the geometry of the polytope there has lots of vertices that you're going through, or are you cycling because of numerical problems?
Yeah, both. Yeah, there are really, I'd say there are two modes. So mode number one is just degeneracy. So you've got a very high dimension face, optimal face. And so in fact, in order to move to a vertex, you basically wind up not much better off than if you just started simplex from an arbitrary vertex. And yeah, there are definitely other cases where you wind up with an ill-conditioned basis. So you try and find you have to start with a guess at a basis. And if that guess basis is ill-conditioned, then these pivots basically, you wind up introducing more and more error until eventually you're at a point where your basis doesn't really capture any of the information that was contained in the initial interior solution. So both of those can happen.
Which parallel sparse Koleski do you use?
We wrote our own.
Okay.
Well, there's some special properties in interior point which we exploit, which make it harder to just go and use a package.
All right, well, if there's no other questions, let's thank Ed again.